Let us now describe the chord tangent process of adding points on elliptic curves. So say we are given an elliptic curve E and we are given 2 points P1 and P2 on it, and we want to add these 2 points. So if these points are not equal, then you draw a line through these 2 points, and this line will cut the curve at a third point Q. Now this is guaranteed by the Bazoo's theorem. So Bazoo's theorem says that if there are 2 curves and one curve has degree m, so this curve is defined by a polynomial, so one curve has degree m and the other curve has degree n, then these 2 curves will intersect at exactly m times n points. So here the line has degree 1 and we know elliptic curve has degree 3. So by Bazoo's theorem we know 3 times 1 is 3, so the line and the curve will intersect at 3 points. So once it intersects at the third point, which you denote as Q, you draw a vertical line through Q. So this line will hit the curve at some point, and the point where it hits, that is the point which is defined as the sum of P1 and P2 on the elliptic curve, and you denote this point as P1 and then you have this O plus P2, so as to distinguish that this addition is on the elliptic curve. So pictorially you have this elliptic curve given to you going like this. So you're given 2 points P1 and P2, so you draw a line through it, so you have this pink line through it. This pink line hits the curve somewhere at Q. So from Q you draw a vertical line, it hits the curve here, and this is precisely the point we are saying is P1 O plus P2. So vertical line means that you are drawing a line from the point Q to your point at infinity O. So this point at infinity, this is our special point on the elliptic curve. So when we defined the elliptic curve, we said that there was a special point. So this special point is point at infinity. So when you draw a vertical line, means that you're connecting Q and this point at infinity. Now if the points are the same point, so P1 is equal to P2 is equal to P, and then you take a tangent line and let it intersect the curve at another point Q. So notice that the tangent line intersects that curve with multiplicity 2. So you will have still 2 plus 1, 3 points. So that is the convention you take. So the tangent line intersects the curve with multiplicity 2. So this is with respect to the Bazoo theorem, you still have 3 points of intersection. So again you take a vertical line through Q, which will hit the curve at some point, and you denote that point as 2P, which is P O plus P. So you have this point P. Through this we are drawing a pink line which hits the curve at point Q. Then you draw a straight line from our point at infinity to Q. It will intersect the curve at some point here, and you denote this point as 2P. For an inverse of a point P, you just take a vertical line through P which will cut the curve at minus P. So you join P with our point at infinity, that is the vertical line, it will cut the curve somewhere, and this is minus P. So some things are obvious from our construction. So if P1 is not equal to P2 and their x coordinates are the same, so then the only line you can draw is a vertical line because the x coordinates are the same. So the only thing which is differing is the y coordinates. So you have to join the y coordinates. So the only line you can draw joining these 2 points is a vertical line. So if you have a vertical line joining the 2 points, then P1 O plus P2 will just be our point at infinity. So if the 2 points P1 and P2 are equal and y1 is 0, then you set P1 plus P2 as 2P1 or 2P2 because both the points are equal. This is equal to our special point, that is the point at infinity. Now the addition on elliptic curve satisfies these axioms. So that is P O plus with special point is equal to P, which is O plus with special point P. This sum of point and its negative point is a point at infinity, as you can see here using this. So P1 O plus P2 is P2 O plus P1 commutativity. So all these are easy to check using our procedure. The associativity, which is this law, this is difficult, and this is quite tedious, and you can see its proof in the book by Silverman, The Arithmetic of Elliptic Curves. So let us now describe this entire process algebraically. So say the points are P1 is x1, y1, P2 is x2, y2, and they are on this elliptic curve E. Y square is equal to x cube plus ax plus b. So then you can connect these 2 points via a line L. So y is equal to mx plus c, where m is the slope of our line. So this point is already given to you. So if you can compute this slope, then you obviously know that c is equal to y1 minus mx1. We just rearrange this. So we have to compute this slope. So the slope you compute in 2 cases. If P2 and P1 are not equal, you have this formula delta y over delta x, so y2 minus y1 over x2 minus x1. If the 2 points are equal, then you have to implicitly differentiate this. So you get 2y dy is equal to, differentiate this, you get 3x squared dx plus a, differential of p would just be 0. So now you compute dy by dx, and this is what you get, 3x squared plus a divided by 2y. Plug in the first point, x1, y1, this is what you get. So if the points are equal, you get this m. So now we want to find the points of intersection. So that is, you want to find this elliptic curve intersecting with our line L. So A intersection L. So the first thing is, instead of y, we put in our mx plus c square. So you put in this line, y equals to mx plus c. So this line we have put in right here, and this is our elliptic curve. This is L because of L is equal to y. So now you take this on this side, and you know this elliptic curve will split into 3 factors. That is precisely because you know the 2 roots. The 2 roots we know is the 2 points which lie on the elliptic curve, x1 and x2. So these are the 2 points which satisfy the elliptic curve. We already know it. So you have x minus x1 times x minus x2, so degree 3 term. So the third point of intersection has to be x minus x3. So this is the third point we want to find. This is given to us. This is given to us. So now if you expand it, it will be x cube minus x1 plus x2 plus x3 x squared, and then bunch of terms here. So notice this is x squared. So this is the coefficient of x squared right here. So what is the coefficient of x squared here? So coefficient of x cube is 1, coefficient of x is a, but coefficient of x here comes right from here, and which you know would be, you will have a term like m square x square here with a negative sign. So this negative sign will get cancelled with this negative sign. You get m square is equal to x1 plus x2 plus x3. This is from equating the coefficients of x square. So now you solve for x cube, bring it here. So m square minus x1 minus x2. So this gives you x3. So that is the point of intersection. So from here you can find y3. So y3, you know, again this formula you use, y equals to mx plus c. So y equals to mx3 plus c. So here the c again you calculate from here. So this is also given to you. So now p1 o plus p2 is equal to x3 minus y3 because of the reflection. So again the only thing you need to find is c and m. So first thing is you compute m, which can be computed by this or this formula. Once you compute m, you plug it in here, you get c. So algorithm step 1, step 2, you get c. So once you get c, you plug in here, step 3, you get x3. You plug c and x3 here, along with them you get y3. Step 5, you put a minus sign and you get p1 o plus p2.